Are you?
Always forget that answer. Okay, so I don't have time for grabbing one poster.
Introduction or anything, or do we just like
roll you out?
This is very short. Yes, you're on it. Yeah.
Whoa, we don't want that.
A little bit.
Oh, you
The other one.
the ones that point up. The ones that point
I'm
up.
also leaving.
No,
Yeah,
I disagree.
Yeah,
You disagree?
I kind of agree with John.
The
contrast on the screen is better with these.
Okay.
Than with the ones that.
Alright.
One of these contractors.
You probably want to get rid of your
Yeah,
this mess.
I don't think
July 5th is the original start date, but I'll probably do part remote, part local.
Perfect.
We'll be in the area at least, probably through September. Yeah.
And I know there's somebody to get rid of that bar on the bottom, but I can't remember what it is.
Certainly a USB-C input to your
Oh, you
laptop.
mean get this away? Or
I thought there was a way, but
I don't know. I don't know.
I don't know.
some stuff.
Or the HDMI.
I have a dongle here that can
you
plug in HDMI.
Yep.
The problem with that was you lose control of that computer, but it's fine because you're hosting Zoom.
Maybe view options?
Well, yeah, I mean, I think it's functional. Certainly, we've done other talks this way, but
Yeah.
Oh, now you have the first laptop, I guess, instead of
Yeah,
movies.
yeah.
Oh, okay. We just get rid of that.
cool. That's great. You need to write that down somewhere.
Okay, so we good? Okay, very briefly, so our speaker today is Jordy Davelaar. He's a postdoc at Columbia in the CCA, and he's part of the EHT collaboration, and will be talking to us today about the recent observation of Sagittarius A star.
Thank you, Chris. Thank you for the kind introduction. Well, the observations were 5 years ago, and I'm really happy that I can finally talk about it to you, because I've been avoiding the question, when do we get the Sagittarius A star results for 5 years now? So I'm very grateful to be here. Please interrupt me if there's anything unclear. I would really like my talk to be interactive instead of just me broadcasting, so please let me know. And yeah, so the star of today is, as Chris already highlighted, of course, Sagittarius A star, which is in the center of our Milky Way. This is the radio view of our Milky Way. And if we zoom in more and more towards the center, like in the 1970s, people found out that there's a very strong radio source there. There's all kind of substructure here, and that is Sag A itself. Very bright, very compact. These beautiful spiral arms where we think that there is material being fed towards, like the actual black hole. And then there is like this peculiar small spot here. If the EHT started to zoom in more and more and more, we started to see this ring-shaped feature, and that is what I will be talking about today. Yeah, my name is of course on the slide, and behind that is that it is on behalf of the Event Horizon Telescope collaboration, because this is absolutely a team of 300 people. So it's really a teamwork effort, and not just from individual people. This was a collaboration meeting that we had where we were discussing the MID7 results, actually, so not the Sagittarius A star results, but there are more than 300 people, not all of them on the picture. 80 different institutions, multiple funding agencies, and a group of telescopes. So I really want to emphasize, like, this really is a group effort, and I'm presenting on behalf of all of these people and not just for myself. So the thing that we've been working on is this large series of papers that dropped on FJL on the 12th of May. So the first 6 here are collaboration papers, which really like explain like the broad results, and then we have like a paper that is a summary of all the results that we presented. We have a paper that goes into the multi-wavelength observations that then coincide with the actual EHT observations. We explain a little bit of the data processing. Then there's a paper fully dedicated to the whole imaging process, like how did we get this bring out of the data, what kind of methods do we use, and what kind of checks did we do. We then test for the variability and the morphology, and we get a black hole mass out of this ring size. We compare the data with numerical simulations, and then in the end we actually test compared to a black hole metric, and also to metrics that go beyond a Kerr hypothesis. So you can think about like Johnson-Psaltis metric, charged black holes, wormholes, and more exotic things like this. And then additionally, we had like 4 papers who were led by people within the collaboration, and the rest of the collaboration is also on it. But these were like instrumental papers that were necessary to be able to do the 6. So we also highlight the people who actually did most of the work in those cases. So as you can imagine, 10 papers, 60 minutes, that's going to be rough. So I had to pick my battles here, and yeah, I have to like highlight a little bit of the results, so I can't talk about all the details because then we will still be here tomorrow morning. So I'll be mostly talking a little bit about the things that I was involved in, and I did on a Blue Monday a little bit of the imaging. So I will tell a little bit about the imaging methods that we used, and I will tell a lot about also the theoretical part, because I'm a theoretician from nature, so I do a lot of these plasma simulations myself and try to compute observables from them. So I will mainly go into detail about 3 and 5, but first let's start off with some actual background before I start talking about the black hole on the right of the screen. So let's step back by 100 years or more. Like, why do we think black holes even exist in the universe, right? Why are they important and why do we care? Why do we want a picture of an actual black hole? So the idea of a black hole actually predates general relativity. When I first heard that, I was actually quite surprised. I didn't learn this in my bachelor program for some reason. Namely, in the 1800s, like people like Michel and Laplace already hypothesized that if you have a star, you make a star massive enough, and if a photon is actually a massive particle instead of a massive particle, you would expect that the star is also pulling the photons back. So if the star is just massive and more massive, at some point your escape velocity will exceed the speed of light. These photons won't be visible to us because they will just plunge back towards the actual star, and these will be what they call dark stars. Well, this was the 1800s. Maxwell's theory wasn't written down yet, but when Maxwell wrote his theory of electromagnetism down, they found out that photons are actually massless. So the idea of a dark star went into the garbage bin and was revived, of course, by general relativity later based on different arguments. But there was already some kind of a notion that there could be objects in the universe where there is some invisibility happening, where we can actually not observe parts of the actual universe. This was, of course, then general relativity by Einstein in the early 1900s, where he wrote down his Einstein equations, and there he posed that, okay, these equations, like 16 coupled differential equations, this is going to be extremely hard to solve. Like, how are we going to ever find an analytical solution? He was very pessimistic about that, actually. And it came to a surprise to not just him, but the community. Like Carl Schwarzschild, like a half a year it took him to find a solution to the Einstein equation, which is now the famous Schwarzschild solution, which I wrote down here for completeness on the slide. And there's also a important thing that I always like to mention here, like from a historical perspective. World War I was raging on in Europe back then, and he was actually fighting on the East Front and deriving this in the trenches of World War I. Like, I cannot imagine a more cruel workplace than that setting, and of course nowadays also, yeah, more relevant.
Friedman did the same thing.
Yeah,
He was Hungary in St. Petersburg when he wrote Expanding Universe.
incredible, really incredible. Yeah, that's
There's
more relevant.
Something about GR.
Yeah, maybe that. So yeah, maybe we will see an interesting new paper coming out in the coming months. Then I don't know. It's more relevant than ever nowadays. Anyway, like with Roy Kerr, it took like 50 years later. It's also to point out like the difficulty of finding these solutions. Like Roy Kerr, it took like 50 years to also get the rotation solution out of the Einstein equations. And with the Kerr solution, we then have like a black hole space-time that can be described by the mass of the black hole, the rotation of the black hole. And this was back then still like, okay, these are like theoretical objects. Can we actually observe them? And after like Kerr wrote down his like rotating solution, people started to think about, okay, these quasars, maybe they are distant galaxies with massive black holes that launch this incredible amount of emission, so maybe black holes are real. And this started people to think like, okay, but if they are real, we can maybe make a measurement of how they look like on the sky. And if we know how they look like on the sky, we can actually test general relativity in the strongest gravity limit you can possibly think of, namely in the region where not even light can escape towards an observer. And then the size of a black hole is set by its event horizon. In the non-rotating case, we call it like the Schwarzschild radius, after the man on the right, of course. But this is not entirely the whole story, because black holes actually also gravitationally enlarge themselves. Like, we don't see the actual event horizon as two gravitational radii or 2gm over c squared, but it's actually a little bit larger, because when light approaches a black hole, it's actually also focused towards the black hole because of the curvature of space-time. It's like nicely illustrated here on the right. So you have like photons coming in from the right and they get like banded away. And then there is like a critical region here where they almost start to circle around the black hole. If they're a little bit further in, they all plunge in it. So if you would look from the black hole from very far away and you would like put a flashlight on it, you would see that like also light that is a little bit higher than the actual black hole is also captured by the black hole itself. So the apparent size of the black hole is actually enlarged because it also works like the other way around. And this is what people started to coin the shadow of a black hole, which is around 2.5 times larger than its actual Schwarzschild radius.
Can you be a little bit more specific here? So this shadow thing. So if there is a black hole Schwarzschild and light is coming like this, obviously because of this bending thing, I will get light all over the place, right? Including like if I am at a finite distance. But apparently this 2.6, whatever, 5.2, whatever you call, 2.6 Rg. This thing is what, like the brightest thing, or what exactly is this 2.6?
Okay, this 2.6. This is coinciding almost with the photon ring. So you either have light rays that start to circle around infinitely, or they plunge inwards.
But
So
do I see total darkness at any direction? Suppose plane wave, black hole, I look like this. Will I see like dark spot in the center of it, or what?
Not entirely, because you also have foreground.
Exactly.
Right?
So no foreground, because some light will certainly be bent.
Yeah.
This way. So this 2.6, is it like the brightest part of this shadow, the darkest part of the?
Yeah. So the photon ring is typically also enhancing the emission because you get like multiple rays that are
so
very.
2.6 is the brightest.
Yes.
Okay.
Yes.
Okay.
Maybe I should have shown this image immediately, because here you can see the thing you were saying, like, right? There's like emission also in the center here, but this is like the ring that we're talking about. And this ring, the size of this ring, this is the critical curve. That is what is constrained by that we can use to constrain GR.
What Andre is asking about, let's say you just had some backlight, the CMB, let's say, how big would
Not
the shadow
CMB,
be?
planar.
Okay, plane wave. Plane wave behind the black hole, and how big would the shadow be at 2.6?
That is actually how Bardeen previously in 1970s computed this. He had like a black hole just moving in front of a star. And then like, okay, what would be the dark patch that you would block out because of the starlight just being bended towards the actual black hole? And then you get this 2.6. If you have like a faraway screen of emission.
Oh, 2.6 is the cross section.
Yes.
Okay, great.
That's a good way of saying it. Yes. Yes. And then the appearance also depends on what kind of metric you put in there. So like here are a couple examples. So this is just like using the Kerr solution, and this is the Jonathan Psaltis or Kerr-Sen, or if you can even go even more exotic, where you put like a boson star which doesn't have an event horizon, but is still compact enough to like mimic something that could be as massive as a supermassive black hole. So like being able to measure an actual candidate black hole would therefore help to figure out like, okay, is Kerr the real deal, or do we need to think about like other space-time geometries that go introduce like exotic physics that go beyond the standard model, or is quantum mechanics already an important thing to think about if you want to look at like event horizon scale images.
So for Kerr, is the dependence on the azimuthal angle?
Yes, yes.
So that's what that's.
Yeah, so this is shown from more from above. So, but if you would look like if you would look in the edge-on view, you would expect that the left side would be very asymmetric because of the space-time rotation. You get asymmetry in the edge. So then there is like a spin dependence. It's not as bright here because they didn't put it exactly at 9 degrees. Yeah.
This analytic wormhole. What is an analytic wormhole?
Yeah, that is a wormhole space-time that people looked at. So they actually put like people like Wojciech Wilgus, they had a paper on this where they also looked at like how an event horizon could look like if you have like analytical space-time that describes a wormhole. So
What's the difference? Why is it different from black hole?
I must admit that I don't know all the details of what he did there. So this is like the further down you get, the more exotic things start to become. So I typically reside in the top left. So yeah, but you can see at least that like for the image itself, like there is some change in curvature, right? So the image morphology becomes smaller. So yeah, I guess there is some different gradient because you need to propagate things, right? So you can't have a curvature that completely blocks out the entire universe. So there's no event horizon because you have to propagate to the other side still. But yeah. So like we have now a reason why we think that we need such a picture. So where are our candidates for this? Well, M87 I won't talk about today. It was a candidate based on also the predicted size, but there's of course a more local supermassive black hole as well. Especially if you look like in the galactic center, you get all these stellar orbits going around. This is observed by people like Andrea Ghez and Reinhard Genzel for like decades. And one of them is like this S2 star, which has an orbit of around 16 years. And they very accurately measured the orbit of this star so that they can deduce the orbital parameters. And if you know the orbital parameters very well, you can infer from that the central mass that it is rotating around. And they measure this with so much accuracy that they actually compute like a black hole mass like to like a % level. So they claim that there should be like a central mass of 4.3 to a million solar masses plus minus 0.012. So we have a very well-known black hole mass which we can put into our models. We then know, okay, if we use the distance, how large should the black hole be on the sky? Then we can compare that with what actually comes out of an observational campaign. And if these are very different from each other, well, then we know something about GR that we didn't know before. But this is of course very hard, but because like you can imagine like yeah, a black hole, it's massive, but it's still very far away. So in the case of Sagittarius A star, we're talking about an object of the size like 10 to the minus 10 radians in the sky. So if you want to measure that with a telescope, you need a very big telescope. And my former PhD supervisor, Heino Falke, in 2000 then posed the idea that, okay, if you use a global telescope like the size of the Earth, and you observe it at 1.3 millimeter, it might just be enough to actually see a different feature. So this is for this global array. This is like what he what it would look like with an infinitely good telescope, and this is what it would look like with a telescope of the size of the Earth. So that got a lot of things going, because this started like the era of trying to hunt for a picture, and actually our first detection.
Can you return to the previous slide?
Yes, of course.
This is something I never understood. So why the hell is it totally dark in the center? There is some gas in front of it which does the emission. Surely it cannot be totally dark.
So he has a spherically emitting cloud here, and maybe it's also because.
Suppose for the sake of the argument, I mostly emit at R equal to 10 Rg.
Yeah.
Then your black hole will do nothing, obviously. Mm-hmm. So there must be some very strong assumption about how the intensity of how emissivity changes with radius, right? Yes. So we have to believe that we are very close to FURG in terms of emission, true?
Yeah.
Okay. And only then we get such huge contrasts.
Yeah. Because in this case, he just like assumes like a power law for r to the -2 for like his emission function. So it just scales with radius
all the way to RG.
Yeah. So it just keeps increasing, as you can like roughly see here. And this is a uniform sphere of emission. So that's also why this one and this one are so vastly different. Because this is a uniform
this is different emissivity.
Cloud.
Okay,
yeah.
okay.
This is a uniform cloud of emission, and then you see that there is more emission here. Because what then becomes important is the path length, right? Because then you see a little bit of darkening because these rays are terminated a factor 2 faster than this one.
Yeah,
because this just keeps going.
So you guys are not denying that it is a very strong function of emissivity.
Of course, and this is also what you see in our GRMXD modeling, for example. Great. Like if you change your emission properties, it will look different. Yeah. And this, of course, connects a little bit to like papers from like Sam Gralla and other people who are also advocating for like we have to be careful, and we are aware. So let's go to like the history of the observations. Like in 1998, there was the first detection led by Thomas Kriegbaum, where he used 2 telescopes to measure Sagittarius A star. And then a little bit closer to home here in the US, Shab Duhlman, the founding director of the Event Horizon Telescope, in 2018 used for the first time 3 telescopes, and in 2018 there was a first publication of the first detection also on the intercontinental baseline. This data, however, was taken earlier, like I think 2015, so it predates the first EHT detections of Sagittarius A star. And this was, of course, all monumental and like necessary to build up towards like this global array that could actually observe Sagittarius A star to generate an actual image out of it. Because if you only have 3 telescopes or 2 or 4, this is not enough because you need more information on the source to generate an image. We do that with a very long baseline interferometry. So how that works is you have like different telescopes, different distances with respect to each other. You carefully measure the same source at the same time. You have a very good clock, so you can account for like arrival time differences in arrival time, and then you compare the signal coming at telescope A with the signal coming at telescope B, and if there are small differences, that means that there is some source performance. Because if you have a perfect point source, it's just a plane wave coming in. If you correct for the fact that one telescope measured the plane wave a little bit later than the other one, it would just look the same. If there is some interference of these waves, so there is actual source morphology, you would start to see differences between these telescopes. And then you can use these differences to invert the problem, to find the inverse, because they are measuring in the Fourier domain. If you invert the data, then you can construct an actual image out of that. Ideally, you would have telescopes all over the world, but sadly, the atmosphere is a problem. Well, for us as a human, not for telescopes it is, because it really limits, especially at 1.3 millimeter, the quality of the data. So there are only a couple of sites in the world that are suitable for this, and in 2017 we had 8 telescopes at 7 sites. So this is the same telescope as Thomas Kriegbaum was using in 1989. You have the SMT, the LMT, and the SMA on Hawaii that was used by Shab Duhlman, JCMT as well. ALMA joined for the very first time in the array as well, which was a big game changer. Everyone who ever used ALMA knows that this power is incredible. And also for the EHT it's incredible because it's a large collecting area, so there's an incredible signal to noise, and it really helps to get all the stations in check and do a beautiful calibration of the whole array. So we owe a lot to ALMA in terms of data quality. And these top ones were used for M87, and for Sagittarius A star we were also able to use the South Pole telescope, because M87 is all the way up in the northern sky, so the South Pole can't see it, but Sagittarius A star can be seen from the South Pole telescope. So we gathered in a 2-week window 5 days of data worth of more than 5 petabytes. I learned at the press conference that that is equivalent to 100 million TikTok videos for who knows TikTok. Apparently that's 100 million TikTok videos, so we made one image out of 100 million TikTok videos. And then there was also the coincidence that we had exquisite weather conditions. Like, I don't know what the probabilities are of having incredible weather conditions at 7 sites at the same time. Like in the years after, we never had it that good as we had it in 2017. That also helped a lot with our actual data quality. So, and this data was then transferred to Haystack here in the US, or the Max Planck Institute in Bonn, where the data was correlated and calibrated. And then, that started the whole process of the actual imaging. So on this slide, I show the data on April 7th. And on April 7th, that was the best day of our array for Sagittarius A star, because of the coverage of the amount of telescopes that could join. So we have the most confidence in the image that came out of the 7th of April compared to other days. For example, on I think April 11th, ALMA couldn't, for example, join. Well, ALMA was, as I said before, the best station in our array. So you can imagine that data is a little bit worse. So as I said before, like the very long baseline interferometry is like a Fourier experiment. So here you see like the UV domain where we show like the measurement points. So UV, that means like the separation between the different telescopes. So as the Earth rotates, the separation between the telescopes also changes. So this is like showing how the EST looks like over the duration over 5 hours. So like telescope here, telescopes here, and then they just slowly move along these tracks and measure different components in the UV domain.
How long does it take ALMA to get signal to noise or what have you?
Oh, that's a good question. Very fast, because here on the bottom, I actually show the light curve that ALMA generated. And these
But what is
include...
it like? How does it compare to the characteristic time of 10 minutes, which characterizes Sag star itself, supposedly?
It's much smaller, because this is the light curve like on our time scale, right? So you see
and
these data points here. These are many points, and these include the error bars. So the error bars are shown.
So it's like 10 seconds or whatever.
Yeah, it goes really fast. And
other telescopes kind of similar.
yeah, because this is the SMA, for example, where you can see the actual error bar. So here it's harder, but for ALMA it's much better. So we also use the light curve that comes out of the ALMA data to calibrate the data at the other telescopes. Because from ALMA we know exactly what the emission should be.
And the light curves copy each other, so
yes,
everything is
because we're looking at the same source at the same
right.
time, it's all at the same moment. So we use this information to get all the telescopes in line. So this is indeed another example why ALMA is very good. And this is then the actual amplitude we measure at pairs of different telescopes. So this is the actual signal that should have come out of this plot if you would have made it 3D. I always like to show it because what you can clearly see here, that there's like a dip happening here, and there's a dip happening here. And if you would take a Fourier transform of a ring-like shape, it would show up as a dipping feature. If it would have been a beautiful point, it would have just gone down, and you wouldn't have seen a dipping feature. So this is already, without even making an image, already a first indication that there should be some ring-like feature in our image if we make an image out of it.
You mean this is the correlation signal?
Yes.
Oh, okay.
Yeah. Exactly.
What's the proper terminology? Correlation? What do we call it?
It's
the interferometry already, right?
Yeah, it's the visibility amplitude.
Visibility.
Yeah. And the visibility then is the cross correlation between two signals from the two different telescopes. So in the colors here then mark like different pairs of telescopes. So these are far away from each other, and these are far away from each other, and these are close by.
So at 8 on the x-axis on the top right panel there, so there's a huge spread in those points, but the error bar on each of the points is less than the spread. So why is that? Is that because the image is changing over time, or?
So this is a 2D polar plot, right? And this is now all of a sudden a 1D plot. So what we do is we like put all the information and we just swap it into a radial plot. So the image is not exactly symmetric in the UV domain. If you would measure it at like different polar angles, there should also be information there. And that introduces a spread also in like how the data here looks like.
So it's the azimuthal dependence, but not the time variation.
Not necessarily, yeah, but there's also time variability on top of that. Because Sagittarius A star is highly varying over time. As you can see in the bottom panel here, like the light curve fluctuates with like 4 to 14% and can change like in a couple of minutes to hours. And this is also why it is so much harder to make a picture of Sagittarius A star compared to this one. So I really like this visual because that the people at the Smithsonian made. So this is a M87. It's 20 billion miles in diameter, much larger than our actual solar system. So if you start shooting a photon around it, this is not for scale, by the way, and it's not the right time scale. Going from here to here would take days in terms of M87. So this is Sagittarius A star to scale with M87. It's 1,000 times less massive, so also 1,000 times smaller than M87 as well. So you can imagine that if this takes days, if you shoot a photon around Sagittarius A star, this is going to be minutes. So going around Sagittarius A star is much faster if you're a photon, which also means that the accretion flow, like the material that's flowing around Sagittarius A star as well, is also going much faster. So there's like a lot of variability during our VLBI experiment. And this is a problem because VLBI typically assumes that your source is static over your track. And in the case of Sagittarius A star, this is definitely not the case. So how to look at our result is then like, it's more like a long exposure instead of like a snapshot.
But cannot you create an image every few minutes?
No, because we really rely on the rotation of the Earth to fill the UV domain. Because otherwise, you would just have a point here and a point here and a point here and a point there. And then there's so many gaps that the image quality becomes really bad.
It would be a crappy image.
Yeah, and even at some points we only have like 2 or 3 telescopes for looking at the source because the other ones are just not in view.
So you must be creating something averaged.
Yeah, or go into an array where you have more coverage at every moment in time, so that you at least probe all kind of scales at the same time instead of like only have large scales or small scales. Because like if you only have Hawaiian view, you have like 2 telescopes, right, who are almost next to each other. Well, if you are looking at Europe and the South Pole, you only have those in view.
So you like create 1 image per every 6 hours or something. Yeah, roughly.
Yeah, or at least one where you can have. That's what we did at the moment. People are working on like using like priors from an average image to generate then like a time varying image, so that you can start like making movies, for example, of Sagittarius A star. It's like these dynamical imaging methods, but that's like still what people are working on. But currently, because of the sparseness of the data, we really do like a long exposure. And then there's another thing that we have to overcome, is namely, if you look at M87, we look out of the galaxy and then right from the top into the M87 galaxy. So we're just peering only through like some intergalactic medium and that's it. But in the case of Sagittarius A star, we have like 8 kiloparsecs of galaxy to peer through. Where there's like a lot of gas and a lot of plasma in between us that's blocking the view sometimes even. But for the frequency that we're using, like 8.3 millimeters, the biggest uncertainty here is that there is some scattering screen which they attribute to like electrons who are like interfering and distorting the signal coming from Sagittarius A star. So this is a simulation here on the left, and this is what it would look like with like the scattering screen in between. So you can actually see that like this enlarges the features a little bit and makes the image a little bit more blurry. And what's even worse, it's like this is also temporal. So the scattering screen is also changing day by day. So there's like some turbulence, electron plasma in between us and the source that is also like disturbing it. So the good thing is that this has been known for like a decade. So there's like a lot of observational constraints on how the scattering screen behaves as a function of time and as a function of frequency. So by using the most state-of-the-art models, we can actually correct for this effect, as well as we can correct for the time variation of Sagittarius A star. Well, then the imaging starts, well, and then people started to make the first Sagittarius A star image, and everything started to look a little bit different, and everything was time variable, and everything was like very hard. And in 2019, we therefore decided to take a step back and to think everything through again. And the first thing is we came up with a large set of synthetic data models that are time varying. So sadly, this isn't a movie, but you have to imagine that all of these here on the bottom are time varying. So you have like turbulent features on top of this. This is actually a hotspot that rotates around on a circle. This is also some turbulent ring. Then we have an actual point source or a double point source, and even a time varying GRMSD simulation. And we have 4 different imaging teams, all using like different imaging techniques. And the way it was set up then is that they should try to be able to recreate like the ground truth images with their method so that it actually looked like the actual ground truths. And that was harder than expected, but after a long time of like trying to restructure codes, rethink like how the imaging procedures work, come up with ways to include the scattering, to include the time variability. People did like massive parameter sets, like they started to tweak around all kind of different knobs and model parameters in their imaging code. But in the end, like the training data, these are like the reconstructed images. So you can see like they get the ring, we get the disk, there's a point source in there, you get like these crescents. And these are generated with the same set of parameters. So if Sagittarius A star would have been a point, it would have shown up. If it is a ring, it would have shown up. If it is a disk, it should have shown up. Based on like, okay, we did a synthetic observation, we used the best parameters, and indeed all of them come out. So if Sagittarius A star would have looked different,
time variability.
these also include time variability.
No, suppose once it's a crescent, then it's a sphere. Crescent, sphere.
Yeah, that is not included in the ground truth. Yeah,
Okay.
that's not in the synthetic data set at least. So yeah, that could have been a different. But as I said, like this is like a top set of parameters. So it's not like only one set of parameters gives an image. So we have like a large set of parameters that recovers all of these. And then for Sagittarius A star, it's a bit similar. We actually have like thousands of Sagittarius A star images, and not just one. And they can be grouped in like 4 groups. So we have 3 groups that are ring-like. They differ a little bit in their morphology. Like this one has a bit of a brighter blob there, and this has like more clear 3 blobs on all sides, and this doesn't even have a ring. And these are all equally valid if you compare them to the VLBI data that we observed. However, they have different sizes in numbers compared to the whole. Like this non-ring cluster, for example, is less than 2%. So most of our models actually show this ring, and it is a ring with roughly a diameter of like 50 micro-arcseconds.
But why are those suspended in space? This is what I don't understand when I look at your image.
Mm-hmm.
Like, I cannot, because your observations cover a few days, you said, didn't you? Within few days, these things should have moved. Why are they hanging over there?
Yeah, because they're, I will show you at the end a comparison with a GRMSD image.
So it's all lensing, you are saying?
No, these are not physical. These are
artifacts. That's what I'm saying. It's lensing. It's just light propagation.
Also no.
Okay.
It is because of the sparseness of our data set again. So this is, I don't have a strong belief in that these ones are actual physical changes in the emission profile. Like we get a ring, that is what I'm confident about.
And that thing is just because of your bad coverage or whatever?
Yes.
Okay.
Yes.
So they are not physical at all?
Yes, that's what my money is on at least, yeah. So as I said, like we have thousands of images, so maybe we should have published it like this instead. Like, there's like a lot of different images going into the final image, which is just an average of all of them. So the features that you see in the final image is more of like, these are the features that we're confident about because they don't average So I would like to go on now to the simulation part. So if there are any questions about the observational part, like maybe now is a good time to maybe make a small stop on questions on that. And otherwise I will continue on the simulations.
If you could go back to the slide where you were showing the Fourier transform and the different kinds of, I think.
This one?
No, I think further ahead. This one, right?
Yeah.
Is the Fourier transform the same in all of them? Like the different points, are they the same? Oh, okay, no, I see.
No,
Like,
there
they're
is
all
some
different.
variation based on what goes in it.
I guess I was wondering if, like, is there an observable difference right now to be able to tell the point source apart from the ring in the spectrum?
That's a good question. Yeah, I'm not entirely certain what is plotted here. If it is like the ground truth bin, the reconstructed, or if it's compared to the actual data. So I have to look that up. I'm sorry. We have to come back to that.
Okay,
Yeah. Yeah.
On this one. No, the one with the four.
This.
No, the one with the four images and the bars.
This one.
Yeah, I'm just how should we be interpreting those bars? Is this something like a posterior probability that the actual thing looks like this? It's like components of the image. Is there any like actual meaning to the fact that there's way more of the ring ones?
Well, I would say that because there are way more ringed ones, you would put more confidence in the ringed ones compared to the point ones. I would say, but then like which one of the ringed ones is more confident over the others, I find a harder story because they're also like more alike in a way.
But it's averaged over all images, right? Because
yeah. This is also an average over all the rings that go in here. This is an average over all the rings that go into this cluster. Just yeah.
They divided thousands of images into 4 categories based on God knows what, and then they averaged within each category.
Yes.
So it's
based on the feature. So this is a more north-based. These have all a more north-based bright spot. These are more like 3 bright spots with like more of an equal emission. So they are like categorized like that.
Can it be interpreted as Andre was saying before, that maybe sometimes it looks like that and sometimes.
No, but that's what the speaker is saying, that it's probably the artifacts of their. It's not time variability. Time independence is assumed.
Exactly. So if you go, I can give a spoiler here to get that elephant out of the room. Like if you take like a GMHD image like this as an input model for the EHT telescope, and you can create a synthetic image based on the sparseness of the data that we have, then you get a spot, and a spot. Well, there's no spots here. So this is truly like these spotted features. Like people started talking, are you seeing plasmoids there or like hotspots orbiting? I'm like, no.
I'm glad I clarified it. I don't have to think about plasmoids.
Not yet. Like who knows later? For M87 it might work.
But
right?
the problem
Then you
really
make a
is that
snapshot.
your telescope is really not a telescope.
Yeah, it's an interferometer, right? So it works not as a real image, but you have to infer some image based on what you find in your Fourier domain. So these 3 dots are really not like a physical thing.
That's why it's telescopic.
Yeah, got about 15 minutes.
Yes. So yeah, let's try to cover a little bit of the theory then as well. So what we perform is GRMHD simulations, general relativistic magnetohydrodynamical simulations. So it's like a fluid approximation in curved spaceline. And how we set it up typically is that we start with like a gigantic donut around the black hole. We feed some colloidal loops in there. We start to kick things off. The magnetic rotational instability starts to generate turbulence. We get like a different magnetic field configuration. Magnetic field is also advected towards the black hole. Due to the space-time rotation, you also start to launch a relativistic jet. It's what we show here. So this is like what, well, besides what people are doing now in kinetic simulations in curved spacetime, like a bit of the state of the art of what people do if they want to model a source like Sagittarius A star. So this gives us information on the density of the material, the magnetic field strengths, the temperatures, and things like this. So that's going to form a template for making images that we can compare with the actual data. So you can imagine, like, you can play around with like what kind of donut do you put in your simulation domain. If it is a small one with a low magnetic field, you get a simulation that says a weakly magnetized accretion disk and torus, which we call like a standard and normal evolution simulations per se. Or you can put a really big disk in there with a strong vertical magnetic field. Just create like a magnetically arrested disk, which gives rise to a stronger outflow, bigger jets. So there's also some ways to play around there. So you can even go even more exotic. You can put a disk in there with an inclination with respect to the black hole spin axis. So your jet shoots out to the side instead of up. Things start to become very different and tilted, and it starts to process around. So this is also included in paper 5. And then we also have a model from Sean Ressler and his collaborators, where they used large-scale inflow based on stars. So they have like a couple of Wolf-Rayet stars moving around the black hole. These are also observed, so they take like the orbital parameters from the observations, and they let the wind of these stars accrete towards the actual black hole. And then they create like a simulation out of that for like the smaller scales. They also provided us those simulations that we can compare to the data as well. But these are all plasma quantities, so this is not radiation yet. So then we use a general relativistic ray tracing algorithms. These are virtual cameras. We put those outside of a simulation domain. The camera consists out of pixels. We assign a wave factor for every pixel in this camera, and we integrate the geodesic equation from the camera towards the black hole, where we take space-time curvature into account. So it's full GR, and then you get like images like this. So again, you have like this ring-shaped model. This is shown a little bit more from the side, so you can also see that the black hole is now more asymmetric compared to the ones that I showed in the beginning, because it's also a rotating black hole. And then it's Doppler boosted because the left side is moving towards us and the right side is moving away from us. I will skip this because of the time. So we have these different geometry simulations that can differ in the amount of black hole spin rotation. Either they're tilted or untilted, and then we start ray tracing them by changing the temperatures in the disk versus in the jet. We start changing the inclination, so we go from 10 to 170 in steps of 10, and we also compute spectra for each of these models, where we include synchrotron as well as self Compton upscattering. So we not just look at radio emission, but also at the X-ray emission. And then we have, I don't have time to go into full details there, but we have models that include thermal electron distribution functions, and also models that include non-thermal electron distribution functions. So then we have 11 constraints in total. We thought of, okay, how can we constrain our models? So here you see like all kind of models here. So first we compare the models based on the ring size that we see. That already dropped some of the models. Then we look at the shape, like does it produce a full ring or only half of a ring? That already gets rid of a lot of models. Then we look at like, okay, the spectrum and the X-ray. Are the models overproducing the X-rays? Then we throw them out. Then we also look at the size at lower frequencies based on different telescopes. And then you end up with like a small bit of the parameter space.
You should have kept going and excluded this too.
Oh, we do. I do in the next slide.
Okay.
Because we have an issue. It's called time variability. So our models have a big, we found a way to rule out models based on.
There was a paper recently by Ressler et al. Claiming that their winds are best in reproducing time variability.
Yeah, so if you use all of these 11, we rule all the models out. If I drop some of these
So you can
and
wrestle
keep
a
the
phase.
time variability, you can indeed have models still. But I think the Ressler models in the paper that we have didn't get the 86 gigahertz emission right. So although they get this right, they don't get this right. So then you still rule them all out if you take the all 11 constraints. Yeah. So this is, for example, based on the EHT size. So this is like the confidence interval of the emission size morphology based on the data. And then the white one is what the emission size is based on the model. So this one nicely fits in within the confidence interval, while this one creates a way more broader structure because the disk is very hot and mostly emitting all the way to larger radii. And then you see that like the size of the ring would have been much larger if this was the case or the size of the emission region would have been much larger in our data. So this one is ruled out based on that. And then yeah, we can keep doing that by, for example, looking at this is a model looked at from more the top, so it's like a 30 degrees viewing angle with respect to the black hole spin axis. This one is when you look from the sides. This is actually a pretty interesting conclusion that comes out of this, because if you compare this one to the data, like I was talking about these dips in the UV radial plot, right? Where I said that, okay, you need these dips to get a ring. Well, this green line here beautifully dips with where the actual data also dips. But if you look from the side, this dip is all of a sudden here, because the emission is so like asymmetric that you more like get like a little bit like a banana or peanut shaped emission size compared to a full ring, and then it doesn't fit the UV data anymore. And so based on our models, we kind of exclude that we're looking from Sagittarius A star from the side, and that the inclination should actually be less than 50 degrees. So Sagittarius A star is somehow pointing towards us based on the models that we have. Well, and then I come here into like, we need to rule out all of the models. If you also add the time variability, we find that our models are too variable compared to the data, or the remaining models that survive the other 9 criterion that we applied are too variable compared to the data. So this is still a bit of an open question, like, are we interpreting the constraints wrong? Are our models wrong? Is there some missing physics that we do not include? Well, we're, for example, using ideal MHD simulations, which means that there's numerical resistivity, numerical viscosity, there's not a physical model included there that actually captures those effects. Well, on the other hand, like MHD is a fluid approximation of the actual source. M87 is definitely a low collision, a collisionless system, because the mean free paths of the electrons are much larger than the actual system sizes. So in a way, a fluid prescription is also wrong. Maybe there are some like kinetic effects that could change things. Another thing is to be able to generate a large library of different simulations. You can't run at like super high resolution for every one of your models. We just don't have the computing power for that. So there could also be a resolution effect here, like that at very high resolution. There are like new papers by Riperda et al. Who do a simulation of 5000 by 2000 by 2000. Well, the EHT does around 250 by 200 by 200. So that's like 10 times more in every direction what they're doing. And they see like beautiful current sheets and plasmoids being generated, which add all kind of new time variability into your simulation that the EHT is currently not capturing. So it could also be that that might change the time variability a bit. Another thing is that the EHT field of view is quite narrow. In the GRMHD, we are also capturing emission from slightly larger scales. So maybe there's some slow varying emission that also changes the time variability. So this is still like an open question. Like the time variability doesn't seem right yet, but yeah, that's for me as a theoretician, it's great because we still have some nice work to do. So if we leave the time variability out, what is then the best region to look for compared to for Sagittarius A star? So everything that is red here is not fitting the remaining constraints. So these are the weakly magnetized simulations, the high magnetized simulations. This is a negative spin, which means that the disk is rotating in the opposite direction with respect to the black hole rotation. So we think that Sagittarius A star is not a retrograde black hole compared to its environment. So we go to the positive spin here. So spin 0 is also excluded. So we also think that Sagittarius A star is at least rotating. And the weakly magnetized models are also all excluded. So the only models that survive are highly magnetized models with a higher spin value, 0.5 or 0.94. Well, we don't have a lot of information in between 0.0 and 0.5, so there could be something lower there as well. And as you look at like these green patches, which are only visible like within like 30, 40 degrees inclination. So we're somehow looking from like 30 or 40 degrees on top of the system. Well, you might find this surprising if you compare this, for example, to a 3 millimeter observations by Isoun et al. 2018. They also say that, okay, Sagittarius A star, if it has a jet, it should better be pointed towards us because we don't see that 3 millimeter. So then you can hide it by putting the jet like towards you. Additionally, if you look at the hotspots in the gravity rotating around, based on their motion on the sky, gravity also infers that the inclination of Sagittarius A star should be below 40 degrees. So in a way, this is all consistent also with observation of Sagittarius A star at different wavelengths. It's still surprising though, because one might argue, like, okay, so the black hole is not dynamically put back into the same plane as the galaxy as a whole. Well, is this expected or not? I'm not sure about that, because that's not my field of expertise. But yeah.
Sorry, if it was aligned with the galactic plane, the inclination would be
90.
90.
Yeah. And we find 30 or 40. So
it should be like this.
Yeah, the black hole spin axis, if you are Earth, is like this. So the disk is like, so the jet is pointing towards you. It's a bit bizarre because this is like almost like it's not a blazar, of course, but if it would have been a little bit more, it would have also almost been a blazar within our own galaxy. And somehow.
Except that it is so dim.
Yeah, yeah. Yeah, it's only 100 times more, 100 times brighter than the sun. It's bizarre. The volumetric luminosity is 100 times the solar luminosity. If it would have been as bright as M87, it would have been 5 times 10 to the 5 Jansky instead of 3 Jansky. So that would have been.
Maybe you mentioned this, but so why towards and not away? What would break that tendency? Or I guess why positive A star and not negative A star?
The negative A star typically it creates an ISCO that's larger, so your accretion flow looks different and a little bit more extended on larger scales. So having it like rotating in the minus solution puts.
So, but the sign is relative of black hole and the disk.
Yes. So also in the GeoMHD simulations, the actual flow looks different. It's not just taking the same simulation and turning it around. No, it's really like the whole flow geometry looks different, and the emission region becomes.
Oh, but they don't know which way it is rotating.
That's what I'm asking.
He's asking whether or not the spin is towards your.
Oh no, that we don't know. No.
They are not sensitive because there is no time variable.
Right.
They don't see them rotating.
Yeah, we don't know the sense of rotation.
It could be pointing 30 degrees away.
But then both the disk and the spin are pointing the other way.
Sure. Yes.
Yeah, that's.
And we don't know the spin of the disk either, right? By any other means.
No. Not that I know. So we don't have constraints on if we're looking from the top or the bottom, because the data is not good enough for that. In contrast, by M87 we could actually make a statement about this, because then we can connect the large-scale jet direction with the point where the jet is in our simulation domain, and then you can break the jet. For Sagittarius A star, there's no real observation of a jet. So. Okay, this one I already showed. So then I go to my very last slide. So this is also the final paper from the 6. So the ring is compared to what Kerr would predict, and if you then look at our ring diameter estimate compared to what Kerr says, then the ring diameter is within 10% of the Kerr prediction. And this is also a little bit better, like this is the posterior compared to like a M87, because the black hole is actually a little bit larger, right? So it's like 52 micro-arcseconds, well, M87 was 42 micro-arcseconds. So we actually resolved the ring a little bit better as well.
So this is what values the spin?
The spin actually changes the ring diameter only by a couple of percent. So our systematics are much larger actually than the deviations that you expect from spin. Yeah, because it becomes a little bit more asymmetric, but in size it becomes asymmetric on this side and then it gets bigger on the other side. So your total ring diameter only fluctuates a little bit. So there's not a very strong balance there on the ring sizes.
But if we believe your previous slide, it is faster than 50%.
Based on the very sparse sampling in the spin domain, yes.
Because the greens were only 50 and 90.
Yes, but we don't have any models in between 0 and 0.5. So maybe at 0.3 you can still get a green dot. I don't know.
I'm kidding, of course. Who believes this?
Yeah. So yeah, let's put my summary up because I think I ran out of time. Thank you all.
What is next for you guys? You have exhausted big black holes as seen from Earth.
That are resolvable. Yeah, so far as we know, that those are the only two.
But on the other hand, it is also beautiful, whatever. It's not gonna die. You will keep like measuring. Or
yeah, that's the nice thing. That is the benefit from us compared to like people working, of course, at live observations. Merger is done. The black hole is one black hole instead of being able to do the test continuously on the same source. So we did.
So they will keep giving you time, and you will observe.
Well, we already have the data. Like in 2018, we had an observational campaign where the Greenland telescope joined, so the array is growing as time goes on, which will improve the image quality as time goes on. In 2022, so this year, we had phased NOEMA joining, which is a series of telescopes in Europe at high altitude. A smaller, broader from ALMA. It's a little bit smaller than ALMA is, but it will highly enhance the credibility of the array when ALMA is not in view. So we have like more and more stations joining, which will help to generate better and better images and maybe get rid of like the 3 dots and things like that and get tighter constraints on GR.
So your prediction, the dots will go away with better coverage.
Yeah, I'm not going to put any money on it, but if I was forced to put money on it, I would put money on the dots are going away. So yeah, so I think like with a better telescope array, these are just more of an artifact type of thing. And there's of course also polarization information on Sagittarius A star that we haven't worked on yet. So getting information on the magnetic fields will also be very interesting, especially because we don't see a jet, but the magnetic field lines might imprint in the polarization of signature that show that there should be one. And that is of course also very interesting because there's no real evidence yet of a jet, so or not, at least not direct evidence. And then doing a time variability, so like a movie of Sagittarius A star, of course, also still a dream of the collaboration to be able to provide.
I have one comment I can't resist. I would bet Wrestler. They took like 50 Wolf-Rayet stars, whatever. I would trust their simulation more than anything else. Even if you participated in this MAD or SAID, I think what quotient is always right.
Yeah, yeah. I really like their method because it's you don't take artificial torus.
Exactly.
Right? You start from something that's physical.
Exactly.
Instead of you start from something that's artificial.
They actually have not coupled 50 with actual wind velocities and with actual positions.
Yeah, I know. Yeah.
Oh, you know this.
Yeah, I know Sean. So.
Oh, okay, you know them. Okay.
Yeah.
So it's...
Yeah, so it's a really promising way of doing this, and sadly we can't do this for M87 because we can't measure stars in M87 in their core, right? So it's only possible to do this for Sagittarius A star. But this is a really interesting way of modeling the system. What is interesting though is that if you look at the small scale structure, it kind of looks like a mat, right? They see these mat episodes also happening if you start to wind feed them, like magnetic fields still build up and it still starts to look like a mat. So although they're not one-on-one
Your
comparable,
transient tori, I believe in.
Yeah.
From time to time you would form perhaps a torus.
Yeah, exactly. Yeah, exactly. Yeah.
Any other questions for Yuri?
Maybe just a quick one. So are there any other observations from additional wavelengths or messengers that would help break some of these degeneracies that you'd expect to happen in the next sort of 5-ish year kind of time scale or foreseeable time scale?
Yeah. So at this moment, we already use the emission at 86 gigahertz. We use X-ray information that is taken simultaneously. So we do use the multi-wave band for constraining the spectra. So as these systems also get more and more advanced and get higher and higher accuracy, that would really help. Yeah, definitely. And also with James Webb, maybe like in the near infrared and things like this, this could also help. And this year, gravity also joined simultaneously. So we also have the gravity experiment that that's of course also incredible because they have a very high signal to noise on the near infrared measurements. So that is also very, very promising.
Awesome, thanks.
Within the context of this 30-degree inclination, can we still explain those Fermi bubble observations, or
sorry?
Is there some explanation for the Fermi
bubbles? Yeah, that's a good question. So the Fermi bubbles were potentially formed during an active phase of Sagittarius A star, like 10,000 years ago. So it could also be that Sag A was just in a different accretion regime than we are observing it now. Especially if you think about like these Wolf-Rayet stars who are like rotating around. But what the rest of the paper also says is that the accretion is typically dominated only by a couple of Wolf-Rayet stars who are close to Sagittarius A star, because they blow the most mass closest to the actual black hole. So they dominate the plane in which the black hole is accreting. So if you can imagine that this like time varying, like 10,000 years ago, it could have been another set of Wolf-Rayet stars, and the whole disk could have been different based on where the inflow was coming from, right? So, but yeah, that is different, or the jet is being bended away, but the fact that we don't have an active jet now also says something about like that the situation when the Fermi bubbles were formed might have been very different from what we're looking at today.
And probably Fermi bubbles would require a much higher rate of accretion.
Yeah.
Perhaps some stupid cloud was passing by or whatever, right? Because current rate of accretion is incapable of creating Fermi bubbles.
It's a starved black hole, right? There's 10 to the minus 8 solar masses per year. This is almost nothing. So yeah, it's on a very heavy diet at the moment.
Hi. Do you also have some comment on this Japanese paper?
Oh yeah, I was almost surprised that I didn't got a question yet. So good that you asked. So yeah, for those who don't know, there is a Japanese paper published on I think the 10th of May, who claim that we are looking at artifacts instead of real rings. And yeah, well, it was 2 days before our own press conference, so we were also quite busy with our own press conference. So I haven't read the paper in full detail yet, but I did talk to some of our EHT VLBI experts. And yeah, what I learned from them is that we have high confidence in our data, and the claims that they make are not entirely correct compared to what we write in our own papers. They claim, I don't know the exact details yet, so you have to like excuse me for that, but let's say like I don't believe that we are looking at artifacts, and they make claims based on using our data in a way that we don't think is realistic or that they should be doing things with. So we were actually quite surprised to see that paper coming out.
Or they reanalyzed your data?
Yeah.
And got a different image.
Well, they see still a ring, but they say that it is based on the prior that we see the ring. So if they change the field of view, where we allow the emission to be in, then they say, yeah, it all disappears, so it's just purely based on the field of view that they put in. And then they even make an image where they say, look, it looks like a jet, it doesn't look like a ring. So, yeah. But we also have 3 other groups who already reanalyzed our data. And they claim that we did do the right thing, and that they also find the exact same results as we do. So there are also other independent groups who made the same conclusions as we did. So of course, yeah, we have to look carefully what they did, and we're still talking internally about like how to reply on this, because yeah, as you can imagine, like last week was crazy. So we haven't had the time yet to look into this.
All your data is public, you're saying. Anybody
Yeah.
can do the analysis.
Of course.
That's very
because
nice.
otherwise we could have put anything here. Like if the Sagittarius A star data came out on the same moment as the data came out. So in principle, you can walk to your computer, download our script, press play, and see that the ring comes out.
I can't, but maybe somebody.
Yeah. In principle, everybody can try. So yeah, everything is public, so it's reproducible. Which is, I think, yeah, this is what should be done with this, right? Because so that people can check. So it's good that they check, but we just think that they made some assumptions that field BI experts in the PhD would never have done because of technical reasons. Yeah.
Cool. Okay, well, let's thank Jordy one more time. If you have other questions, you're around.